Last time I introduced this idea of the rotation matrix, the direction cosine matrix, and how it's used. Just to remind you, and maybe to give some kind of vivid idea of how it would be used for a satellite. Here's the Earth, and let's get us a satellite. So here is a situation. We need some reference inertial frame. So we'll use some Earth-Centered Inertial frame. And then we've got a spacecraft fixed frame, some kind of body fixed frame. But if you want to know what direction, let's say, an instrument on the spacecraft is, let's say you've got a frame fixed in the body that you know about. You've picked some directions in the body and attached B1, B2, B3 to those. And then the instruments are going to be located at different spots along the body, meaning they'll each have some position vector. So here's a position vector. Maybe we'll call this point O. And then this instrument we'll call P. So there's a vector R, which is P with respect to O. And this is, of course, written in a body fixed frame. So the B frame. If you want to know, given that this satellite's going to be moving around, rotating, if you want to know where that instrument is pointing, or at least where it is with respect to the end frame, then it's as if you parallel transport the end frame so that now think of them as having a common origin. And then remember how we wrote things last time. This B represents a vectrix of the unit vectors, B equals Cn. Or if we were to write it in the explicit frame labeling way that the book sometimes does, the B unit vectors equals a matrix that we'll call Bn. It's just another way of writing the same thing. This was shorthand for what looks like a column vector, but made up of the body fixed frame unit vectors. And then the C matrix, right? This is just a matrix. So it's got 9 entries. So I'm using this usual convention for labeling the entries of a matrix, C33. And then again, the vectrix notation showing the n unit vectors. If we want to write what that position P is, so R, P, O, that's written in the body fixed frame. So maybe we'll call this, I'll just call this R, B1, RB2, RB3. That means it's the 3 components. If we want to know what these are, Rn1, Rn2, Rn3, so what that is in terms of the inertial frame, then we use what we developed last time, and it would be C transpose. So you would write C transpose, the C matrix times the location of that point P as seen in the B frame. So this would tell you where your instrument at point P in the body fixed frame, the satellite fixed B frame, is in terms of n frame components. In general, C is going to be something different at each moment in time. So even though I haven't said, oh, C is a function of time, C will be changing with time, meaning all of the 9 entries will be changing in time, which represents just how these, here's the satellite. The satellite moves around or rotates, maybe due to controls, or maybe it's tumbling out of control. I don't know. Something happened. But this will in general be turning. Maybe you have it turning specifically to be pointing at a certain spot on the ground, which means for it to do that, it's not going to be keeping the same static orientation. It's actually going to be turning as it goes around. So in general, the orientation of the spacecraft with respect to some inertial frame is going to be changing. And often we call that the synonym for orientation is the attitude of the spacecraft with respect to an inertial frame is changing with time. And it's going to be changing in time due to dynamics. You could say this will be due to rigid body dynamics. And what do rigid body dynamics do? Rigid body dynamics, it affects the angular velocity vector. So when we get into rigid body dynamics, we'll be solving for how is the angular velocity vector changing in time. We'll come up with differential equations that describe how these components are changing. But for now, just know that this is changed by dynamics, and then in some sense the C matrix, the rotation matrix, the direction cosine matrix, encapsulates rigid body kinematics. How is the thing oriented? So with that, let me give you some other ways that we're going to deal with this. I guess the first thing will be to write how is the C matrix changing with time, given, let's say you were given a time history of how omega is changing in time. And so given the book calls it the time history, this would just be how the thing is changing due to dynamics. So the angular velocity vector, omega, how does the orientation matrix, attitude matrix, rotation matrix change with time? Unfortunately, it is not terribly straightforward, and that's what makes rigid body dynamics harder than the translational dynamics. Like how is the center of mass of the satellite moving? That's a piece of cake compared to the orientation of it. All right, so how does this change with time? Now there's a trick that's often done, and it'll be obvious later why we do this, but we write it's convenient to write omega, the omega vector, in terms of the body fixed frame, meaning in terms of body fixed frame components. So that means when we write omega, we're going to be writing it in terms of the B frame. So when I write omega 1, omega 2, omega 3, what I mean is this is the components with respect to B1, B2, B3. We can even write it this way if we want. We could even write it in the vectrix notation. The vectrix notation would say this is omega 1, omega 2, omega 3 times the vectrix B1, B2, B3, where the vectrix looks like a column vector and the components omega 1, omega 2, omega 3 look like a row vector, just to make this work out. That's that. If we want to know how is omega 1 changing in time, and this continues from where I ended last time. I'm going to do a little bit of repeat because I didn't get to finish. It's always nice to have a picture in mind of what's going on. We've got these body fixed directions, which in general are moving around in time compared to inertially fixed directions. And so we just sort of overlay them as if they have a common origin. And what will omega look like? Hey, look, I have an orange omega vector. Maybe I'll do orange. Orange. So here's omega. And it could be changing in time. And omega, we could remind ourselves what this is. Omega b with respect to n. And like I said, we would write this, we'll typically write, we have a choice. We could write this in terms of the n frame components or b frame components. We're going to choose to write it in terms of the b frame components. But first, let me go over this. To write how the directions are changing in time, we're eventually going to get a differential equation for the C matrix. So it'll be a matrix ODE. But the step towards getting there is we first look at, with respect to these n frame directions, how is each of the B frame components changing in time? So let's start with B1. To calculate this, we use the transport theorem that we've now used for several weeks. So it would be just straightforward application. It's going to look like this. We would write things that way. And with respect to the B frame, the B1 component isn't changing, so that's 0. So we're just left with this other term. And instead of writing omega with the subscript bn, I'm just going to call it omega. It's the only omega here. So we've got that. All right. Now we could do the same for B2 and B3. But first, let's do a little bit more work with this. Okay, I've said before that you can write cross products in terms of a matrix multiplication, and that matrix multiplication would look like we call that whatever the vector is. Instead of a line over it, we just put a tilde, and we get the same kind of thing. So we write omega tilde times the B1 vector. And what is omega tilde? So this is the same thing that is in chapter 3. It defines this. I defined it, I think, in lecture 4, just to make your life a little bit easier. This is omega 3, negative omega 1, omega 2. Once you get it memorized, then you won't have to look it up. But right now I have it written in front of me. So it just takes elements of the omega vector, omega 1, omega 2, omega 3, and places them in this skew-symmetric matrix in such a way that when you do matrix multiplication with this, you get the cross product. Okay, so that's omega tilde, and let's just write it out here again. Omega, negative omega 3, omega 2, negative omega 1, and then on the other side of the diagonal, we flip the signs. And what is B1? Well, B1, written in terms of, I guess it's, if it's not understood here, this is all in terms of B-frame components. So I'll put a little subscript B. And what is B1, written in B-frame components, as a column vector, just looks like 1, 0, 0. That's not too bad. All right, so now when we do the matrix multiplication of this, what will we get? We'll have 0 in the first component, and then omega 3, and then negative omega 2. And this is all in the body fixed frame. And we should write it out this way. We'll write it as omega 3 in the B2 direction minus omega 2 in the B3 direction. And then we'll write this in the vectrix way. What does that mean? Well, there'll be 0, omega 3, negative omega 2, B1, B2, B3. That was all just to get for B1. I mean, I did some things carefully there. If we do the same for the time rate of change with respect to the inertial frame of B2 and the time rate with respect to the inertial frame for B3, we'll get different rows. Okay, so for like this one, for B2, we will get negative omega 3, 0, omega 1 times B1, B2, B3, the vectrix notation. And what about for B3? We will get omega 2, negative omega 1, 0 times B1, B2, B3. And then we can combine all of these. Instead of keeping them all separate, we could summarize it. And now I'll use this symbol, the B symbol, if you forgot what that meant. B just means B1, B2, B3, stacked up in a column vector. So the time rate of change of that B vectrix is equal to, if we look at these rows, this is the first row, this is the second row, this is the third row, and compare with omega tilde, it looks like we've got negative omega tilde. So this can be summarized as negative omega tilde times, well, what's it multiplying? It's multiplying the vectrix b. So the book glosses over how it got this, but this is equation 3.24. So we're not done yet. We haven't yet written this in terms of the C matrix, but we will. So now that we have this, we can substitute in that the B vectrix equals C matrix times the N vectrix. So we're going to substitute in that B equals C N to both sides. Okay, so we're looking at this equation up here. The left-hand side, time rate of change with now the C matrix times the N vectrix. And the N vectrix is just all of those N directions. So now we would do a product rule. We first take the derivative of the C matrix, and you might wonder, well, what happened to the derivative with respect to the N frame? Well, the C matrix isn't in any frame. It's just a collection of 9 scalars, collection of 9 numbers. So we don't have to put any superscript that says that this is the N frame. And this is times the N directions plus C. And now that we will have something that's related to some vector directions, we keep it in there. So this is the derivative of the N directions with respect to the N directions. So that's another big 0. Okay, so we're just left with this for the left-hand side. Okay, what about the right-hand side of this? The right-hand side is negative omega tilde, and we just substitute in what the B vectrix equals C times the N vectrix, or the N directions. All right, so combine them, and we get d by dt of the C matrix times the N directions equals negative omega tilde C, the N directions. And since this must hold for any frame, any inertial frame, you could equivalently just see it as the ends cancel. So we don't need to get fancy. So we're left with a matrix ODE. So the time rate of change of this matrix equals another matrix. It's omega, the omega tilde matrix times C. And this is, if I was to find out where it was, it's somewhere in the book. Yeah, it calls it 3.27. We might just substitute in that all of these are going to be functions of time generally. So the C matrix is going to be a function of time. Omega, because the omega vector could be changing in time due to dynamics, rigid body dynamics. So that could be changing in time. So that's what we have. All right, this would be called the kinematic differential equation for rotations. So this would tell you how is the orientation of the body fixed frame changing with respect to the inertial frame based on what omega, the omega vector is. You take that omega vector, turn it into this omega tilde matrix, and then this is a matrix ODE. And you might be like, what's a matrix ODE? Well, you might see has 9 components. So this is just shorthand. This is the matrix ODE, but it's just shorthand for 9 scalar ODEs. And it's easier to implement in MATLAB or something that's based on matrices. So for example, if you worked out, what does this give you? It'll give you like the C11 component. So the component in the upper left, just put a dot over it, changing with time. The way that changes in time is C21 times omega-3 minus C31 times omega-2. I'm not going to write all 9 of them. This is just giving you an idea. This is what it represents. It represents, this matrix ODE represents 9 typical ODEs. So this would tell you how is the orientation changing, and you could then figure it out. And we're leaving it for later to find out, okay, well, how is omega changing in time? I want to know. Now, this matrix equation could actually be solved. There's, especially in the past decade, there have been new methods that do solve it. The book says that this isn't typically solved, but things have changed maybe since the book was originally written, and it can be solved. It isn't the typical way that the C matrix is represented. We usually represent the C matrix in terms of Euler angles. Euler angles are fun. Well, I don't know. Euler thought they were fun. So yeah, this is, instead of carrying around 9 parameters, you don't actually need 9. And what do I mean by the 9 parameters? The 9 entries of this C matrix. You don't have to carry all of those around. So we can parameterize. In fact, much of the rest of this chapter is on different ways to represent the C matrix in terms of a smaller set of variables. So one way, a common way that's initially introduced, although it, as we'll see, it may not be the best for all applications, is to parameterize the rotation matrix with 3 Euler angles, or we'll just say Euler angles. And Euler angles are a set of 3 angles. So what is meant here? This would be, we write the C matrix, which remember is Bn. This matrix, this rotation matrix, can be thought of as the result of 3 successive rotations about pure body axes. And the most common one is yaw, pitch, and roll. It's probably better. I'll show you a video, and then we'll go through the details of how to derive it. So this is used a lot in aircraft and spacecraft. They're sometimes called the Tate-Bryan angles. But this is showing yaw, positive pitch, and positive roll. And that the end state is like the final, or it's the actual orientation of the aircraft. But you conceptually think of it as the body fixed axes are aligned with some inertial axes. In this case, the things labeled X, Y, and Z, and you do 3 successive rotations. So in this case, first a yaw rotation, which is a rotation about the Z direction. And notice the Z direction is pointing down. And then a rotation about the new Y direction through an angle theta, which we call the pitch. And now the nose of the spacecraft, which is the new B1 direction, we do a rotation about that B1 direction through an angle phi, the roll. It's fun to see. So we'll go through how you get the, all we really want is to represent this final orientation in terms of 3 angles. The end result will be that C matrix, each of the 9 entries is going to be some function of these 3 angles. It's going to be a big mess of sines and cosines, but it helps conceptually. There's a picture of a spacecraft in the book, which looks like it comes from the 70s version of Battlestar Galactica. There was like an early 2000s version of Battlestar Galactica, and I think they had different ships. The first series, which was like 1978, capitalizing on the recent success of Star Wars from 1977, they made a TV show, Battlestar Galactica. So there's a spaceship. I have my own Lego spaceship here. Check it out. It even has vectored thrust. Wow. But so the reason I have this is I'm going to attach a body fixed frame to it. And since it's Legos, hopefully things will work. Let's see if I do it this way. Do I get something? Oh yeah, that worked. Seems to work. Okay. So just like in the picture here, the convention is that you've got B1 sort of in the front, pointing toward the nose of the aircraft or spacecraft. And then the B3 direction points down. And then to complete the right-handed coordinate system, B2 points to the right. So there we go. I've got some a body fixed frame that matches the convention for craft. It's not so obvious if you have some kind of weird satellite, like, I don't know, what's down. But for this thing, there's an obvious, you sit here, you go forward. So there it is. This is gonna break, pretty sure. We take this frame and conceptually we assume that it is initially lined up with an inertial frame. And then we do 3 rotations. So the first rotation is about the B3 axis. And by that, I mean it's the current B3, because B3 is going to change directions after one of the other rotations. So we do a rotation about the B3 axis by an angle psi, which we typically call the yaw. And it's in the positive sense. So here's my 2 frames aligned. Positive yaw would mean I have to use my right hand and the thumb points in the direction of the axis of rotation. My fingers curl in the direction of positive rotation. So a positive yaw would mean turning to the left. No, sorry, turning to the right. Turning to the right. It's positive yaw. I mean, you could define it. If you had a negative yaw angle, then you'd be turning to the left. Positive yaw is to the right. Okay, and then once you've done that rotation about B3, notice that B1 and B2 are in different directions. In particular, B2 is in a different direction. So I would say that's the new B2 direction. And I'm going to now rotate. The second rotation will be about B2 in the same sense. So thumb pointing in the B2 direction, my fingers curl in the direction of a positive rotation. So positive rotation would be pitching up is positive. Let me write that. And we'll look at this from a different point of view too. We'll show each of these in sequence. So the second rotation is about the B2. And by that, I mean it's the new B2. Because that first rotation changed where B2 is pointing. So this is by an angle theta pitch. The third rotation. So after the second rotation, B3 and B1 are in different directions now than they were originally. Originally, we're thinking this is aligned with the end frame. But now the third rotation is about the B1 axis. And again, this is the new B1 by an angle. And the typical notation is to call it phi. That's roll. And that's not how you spell pitch up here. So the final one is roll. Maybe it's worth looking at that video again. So, okay, first rotation about the B3, and then second rotation about the new B2, and then final rotation about the new and final B1. So that's the sequence. And any orientation can be described by some combination of these three angles. So let's look at it in more careful detail. So let's get another figure that just sort of goes through each of the rotations. Okay, so this is showing in the upper left, this is where we're starting. We're starting with the B frame and the N frame are aligned. And then we do a yaw about B3. And this is through an angle psi. Maybe I'll show it like that. So a yaw, angle psi about B3. And then once you do that, you've got the B3 direction is pointing in the same direction, pointing down. B1 is in a new direction. So maybe we'll call this B1 prime. And this is B2 prime. So that rotation, we could write it in a certain way. We could write it, if we use the sort of table way that we've written things before, this would be along the top. The first rotation, we've got N1, N2, N3, and we've rotated to some new directions, which it's B1 prime, B2 prime, and B3 prime, although B3 prime is the same as B3. In this table, each of the entries is going to be the dot product of those two vectors, but I'll just tell you what it is. It's cosine psi, and then this is sine psi, negative sine psi, cosine psi, 0, 0, 1, 0, 0. So this looks like a matrix that describes a rotation of, in the book's notation, it would say a pure rotation about the number 3 axis through an angle psi. So that's the first rotation. Then the next rotation is a pitch. Pitch is, I used green. So we'll do a pitch about the number, this B2 prime direction, right? That's this direction over here. So if we pitch about that, then that direction stays the same. B2 prime stays the same. We'll label this frame with double prime. So this is B2 double prime. It's the same. This is B3 double prime, B1 double prime. And then there's our angle. If we were to, now we write B1 prime, B2 prime, B3 prime. We're going to do another table. And here's B1 double prime, B2 double prime, B3 double prime. And in each of these, this one isn't so obvious. Like, how do you write a pure rotation about the number 2 direction? Well, at least we know that at least the middle entry is 1. B2 prime equals B2 double prime. And then there's zeros. And the rest, I don't expect you to know how to get these. But if you were to take the dot products and figure out what those are in terms of this angle theta, this is what you would get. So this matrix, this is a pure rotation matrix about the number 2 direction through an angle theta. Now the final step, we'll do a rotation about the B1 double prime. So we will do a roll about B1 double prime, which is like the new and final B1 direction. We use blue for this. So roll through an angle phi. So that means this direction, B1 double prime, becomes B1 prime. And there's our angle phi. So the way that we describe B1 double prime, B2 double prime, B3 double prime. The final one is just called, we just called it B, because that's really the body fixed directions. This is what we've been trying to get to, right? We're trying to go from these n directions to these B directions, B1, B2, B3. And we're doing it through this succession of 3 rotations. So this is a pure rotation about the number 1 direction. And what is it? This is so the B1 is the same as B1 double prime, and then there's zeros here. And then we've got a rotation matrix in this lower right-hand corner. So cosine phi, sine phi, negative sine phi, cosine phi. And this pure matrix of rotations about the number 1 direction through a roll angle phi. And these matrices are defined somewhere in the book. Yeah, it's equation 3.32. So if you're getting confused, I'm trying to match Schaub Junkins notation. So, okay, now that we've got these 3 matrices and we're trying to go from N1 to N2, well, here's how we would do it. We would say the B prime vectrix equals M3 psi times N, and let me use green, I guess. B double prime equals M2 theta times B, the B prime vectrix. Then B body fixed directions are equal to M1 phi times B prime prime. And now substitute in. I'll write it with this one. So we've got this. What's B1 prime prime? B1 prime prime is M2 theta times B prime. So we've got M1 phi, M2 theta. And what's B prime? Up here, we write what B prime is in terms of N. M3 psi N. So notice the order of the matrix multiplication. Matrix multiplication, so we were thinking of this as a sequence of first a rotation about the number 3 axis, and then the number 2 axis, and then the number 1 axis. But in terms of matrix multiplication, it looks like 1, 2, 3. Okay. So we can combine all of these and say, well, this is the C matrix. We just do matrix multiplication, and like we talked about last time, if you take the matrix product of rotation matrices, that's another rotation matrix. Okay, so this is the C matrix, and maybe we'll explicitly write it in terms of yaw, pitch, and roll. Yaw, pitch, roll. So there we are. You can write the B directions that way. So we can just remind ourselves, what is C in this case? It is, and maybe it's easier to start from the outside in, because that's just how it works out. It's 3, we first do a rotation about the number 3 axis, and then the number 2 axis, and then the number 1 axis. So this is how you would write the rotation matrix for yaw, pitch, in terms of yaw, pitch, and roll. So this is how we would say the way to write is the C matrix is parameterized by yaw, pitch, and roll. Yaw, pitch, and roll, psi, theta, and phi. And you could work out what this matrix multiplication gives you. It's not pretty. It is not pretty, but you could work it out. No one's going to expect you to memorize this mess of sine, cosine, but there it is, right? So this shows how those 9 entries aren't independent of each other. It just depends on 3 parameters. Now, the yaw, pitch, and roll is a very common set of Euler angles, but it's not the only set of Euler angles. There's others that might be useful in different circumstances. So yaw, pitch, and roll is just one of many Euler angle conventions. The conventions are described by the axes that you use. So what's the sequence of axes? That's it. So there are actually, there are 12 different ones. Although I've only seen 3 of them ever used, and I don't know. If you ask me, well, why would I want to use one versus the other? I don't know. But the 12 conventions are, they're described by about which axis. So we say you do a rotation about axis in this sequence, and it's about axis alpha, where alpha is 1, 2, or 3. And then, so this is the first, and then the second one is about axis beta. Beta again is an integer, 1, 2, or 3. And then the third is gamma, which is 1, 2, or 3. So it's about that axis through an angle, and we just write this theta 1, because that's the first rotation. Theta 2 is the second, and then theta 3. So if we were to write this out, then in general, writing the C matrix in terms of alpha, beta, gamma, it'll be a function of theta 1, theta 2, and theta 3, but it's in a reverse order, right? The way that you write the matrices. The first rotation appears on the right side. So this is m through an angle alpha. Sorry, m about the axis alpha through an angle theta 1, right? It's pure rotation about axis alpha through angle theta 1, and then pure rotation about axis beta through an angle theta 2, and then pure rotation about the final axis, gamma, about an angle theta 3. Okay, so that's it. Now, what are our choices here? Why did I say there's 12? Where did I get that? Well, for alpha, for that first rotation, we have 3 choices. All right, it could be 1, 2, or 3. For beta, we can't do the same axis as alpha, so we have to do one of the other 2. So we only have 2 choices. So the ones that aren't alpha. One of the 2 that's not alpha. That's not. And then for gamma, we can't do the same as beta. We could do the same as alpha, because that direction, that axis, will actually be in a new direction. So 2 choices again. Say just not beta. So then where do I get 12? 3 times 2 times 2 equals 12 conventions. And they're labeled by alpha, beta, gamma. So for example, what we call yaw, pitch, and roll is, since we went rotation about the number 3 axis, number 2 axis, and number 1 axis, this is called the 3, 2, 1 convention. There's other conventions. There's other conventions used in spacecraft, like 3, 1, 3. So that one starts out the same. It's a rotation about the number 3 axis. And then instead of doing the number 2 axis, it rotates about the number 1 axis. And then for the final one, the number 3 direction will have changed where it is. So you could rotate about that again. If I show you a rotation this is for something that looks like a spacecraft at least. So this is the 3, 1, 3 Euler angle sequence. So it starts out, right, the body fixed frames aligned with the end frame. Then we do a rotation about the number 3 direction. And now a rotation about the number 1 direction, this x1 axis. And then another final rotation about the new number 3 direction. So this is 313 used to describe the orientation of a spacecraft. The place where you've probably seen this is in describing the orbital plane in orbital mechanics. So orbital mechanics uses the 313 for orbital elements to describe the plane of the, to describe the orbital plane. And I've even used labeling. Instead of calling it theta 1, theta 2, and theta 3, use the same labeling as orbital mechanics. Right, so in this case, so this is a 313 example, and we've labeled it as theta 1, the first rotation, is omega, the longitude of the ascending node. And then the next rotation should be about the number 1 direction, and that will be inclination with respect to whatever the inertial reference frame is, and then theta 3 omega, argument of periapsis. So it means that B1 is pointing in the direction of periapsis. This is just describing unit vectors, not like the magnitude of the eccentricity. So this is the direction of periapsis. Remember the close approach point. B3 is in the orbital plane normal. So that's the normal to the orbital plane. And then B1 completes the right-handed coordinate system. And B1 and B2 span the orbital plane. So B1 and B2 span, meaning they define by their directions the orbital plane. So I don't know if they told you that a particular convention was being used. There's other conventions. Some of them are used for different situations related to gyroscopes. I've seen the 3-2-3 convention, which is easy to remember because I used to have an old car called the Mazda 323. Had nothing to do with Euler angles. And then some books will give these ridiculous names that make no sense. They'll call them like type 1 and type 2. And then they won't tell you what the convention is. So you need to be careful if you read other books. They'll give them names that are not descriptive. So what's nice about the Schaub and Junkins is they have this unambiguous. They even have an appendix of Schaub and Junkins has the C matrices for all the conventions. So for example, for C 3, 2, 1, theta 2, theta 3. They write it with a shorthand notation. Otherwise, you just get overwhelmed by sines and cosines. And all there is sines and cosines. There's no tangents. So the shorthand here is that C of an angle means cosine of that angle, and S of an angle means sine of that angle. But it's got all of them. Yeah, this is, I don't know if it's still appendix C, but right, it's got the conventions, all of the conventions. So 3, 2, 1. It's just doing matrix multiplication of those pure rotations in different sequences, and you get this. Now, there is a problem with the Euler angles. You could describe every orientation of the spacecraft with it, but it may not be unique. And this is a known problem with the Euler angles, and that's why we'll also talk about other conventions that don't have this problem. There's a problem with Euler angles. And this is true for all of the conventions. So this is, I think this is mentioned, yeah, on page 94. So all 12 conventions have geometric singularities. These are where angles are not uniquely defined. So it's probably good to think of a yaw-pitch-and-roll example. So yaw-pitch-roll has this problem at a pitch of pi over 2, or 90 degrees. So if I think of, here's my spaceship. If I pitch up 90 degrees, so there's going to be a problem. Suppose I'm doing yaw, pitch, and roll. I do 0. No, I'll do a yaw 45 degrees. Bzz, pitch 90 degrees. Bzz, And now I don't do any roll. I have a certain orientation of this spacecraft, right? But I can get that same orientation if I did no yaw and then pitched up by 90 degrees. And now I do a roll of negative 45 degrees. I get the same orientation. So that means even though this is a unique orientation, it is not uniquely described by the Euler angles. So that's a problem. What was that example I gave? And you could double check because the book has something different. So if I have if pitch is equal to 90 degrees, then I could do one of two things. Do a, what did I say first? Yaw of 45, and roll equals 0 degrees, or yaw of 0 and roll of negative 45. And I think I get the exact same situation. So that's not good. So that's a problem. It'll show up when we, because eventually this will show up as a geometric singularity or a mathematical singularity. Mathematical singularities mean when you have 1 over 0, and then numerics blows up. All of our sensors and control schemes blow up. This will manifest itself when we get to the kinematic differential equations in terms of Euler angles. Up above, the kinematic, I'll write it KDE, the kinematic differential equation was this. But when we write this in terms of Euler angles, what we're going to get is, this would be like theta 1 dot, theta 2 dot, theta 3 dot, written as a column vector, will equal, it's not going to be as simple as just writing omega 1, omega 2, and omega 3. There's this weird matrix in front. We'll talk about that next time, what this weird matrix is. But the weird matrix always has some problem. It always has some singularity at particular values. Like for yaw, pitch, and roll, it would be plus or minus 90 degrees, which means you would want to avoid those if you're going to use Euler angles. But later we'll get to other parameters. So that's it for today.